So today's discussion is quite interesting. Like a few days back, one of your classmates asked about that stability of uh, like equilibrium. But here we are going to discuss kind of means we'll study different types of stability and we'll discuss it in detail. So today I am going to discuss internal stability. So what internal stability deals with, uh, it actually consider that when you do not apply any input to your system, then how the state equation or the state response behave. So precisely saying it is the zero input state equation that is only driven by your initial condition. As you can see that I have written as per your request. Now I am ready with all the equations. Like here, let me use a few color to make it somewhat colorful, otherwise it will become a very boring and kind of pathetic. So this is our linear state equation. It is very clear that we are not mentioning any kind of ut here. Only this one is present, and we are interested that what would happen to our state equation solution xt when our t tends to infinity. So how this will behave, that precisely the asymptotic behavior. So now that like we'll be more interested in finding out the bounds on these equations, and also that in some cases that bound will look for a kind of bound, or that we can ensure upper bound of our like solution. Now what I am trying to say that, like, what is uniform stability? Now if I say the word uniform, what comes in your mind? The word uniform, that tells you what? Uniform tells you that, like, if I say uniform distribution of temperature, uniform distribution of money, uniform distribution of everything, that means it is independent of your coordinate. Now here in this case of state, you can consider that or independent of your means that input variable, you can say in other way. Now in case of uniform stability, when we are considering for state equation, the uniform stability is something where the boundedness of solution, like when you are talking about a stable solution, what means image it invoke in your mind, it is kind of something that is, if I ask you to draw the a bound solution, it is like, say this is t. Now we are having, say this is our xt, this is x naught, this point is x naught. So we are having some this kind of curve, but what you can say that in terms of bound, say this is 10, this is minus 10. So From this curve, what we can say that mod xt is always less than 10. So this 10 is see, this bound 10 is independent of your time. But if we consider a bound something like here, say then you will see that for some point this bound gives you the correct value, that is the solution absolute value is upper bounded by that given bound, and in few cases the bound fails to or that bound fails to comply with the requirement. So basically when we are talking about internal stability means we are having one initial condition, and from that our trajectory starts, and then we see that how the trajectory means transit from one time to that next time, and then we'll look for a bound. Now here uniform stability is what we'll see, or we can say that this equation 1 is called uniformly stable if there exists a finite positive constant that is given by your gamma such that xt, that norm of xt, is less than is equal to gamma norm of x naught. Now here one question may comes in your mind that means which norm we are talking about, like it is the first norm, second norm, or infinity norm. Let me tell you one thing, that there is a property of norm that norms are equivalence, means like means in most of the cases, like if someone one norm is greater than the another signal norm, then it implies that two norm will also comply with that same thing. So now this is the actual graphical representation that I have tried to make this understanding simple. Like you can see that gamma is a positive constant that is depending on x naught. We should get an information about gamma. Gamma is only a function of x naught. We are drawing this gamma. Now we have two different initial condition. One is at t naught, another one is at t naught cap. For t naught we are having this trajectory, and for t naught cap we are having this one. But what we are having here, that we can see that both of them are upper bounded by this gamma x naught. So one thing I would like to make it very clear, that like not only two, for uniformly stable system we can have numerous other other initial condition, but all the trajectories must be upper bounded by gamma, correct? So this is like if you look for a non-uniform stability concept, then I would like to explain it with the equation like this one. So clearly this is our AT. Huh? This is a single variable case, so this is our AT. So if you solve, you will get this one. Clear? Now you can see that for a fixed t naught, it is easy for you to find out means for one particular t naught you can find out gamma. for a given T naught, the gamma exists, right? But then what is the problem here? That the problem is like it is dependent on your now uh, the state equation is not here uniformly stable. Why? Like with fixed initial state x naught, let us consider a sequence of initial times t naught is equal to 2k pi. So respective solutions at times pi unit later will be taking these values, right? So clearly we cannot find so here you can see that we are taking these values and will not getting any gamma that is independent of k, but here we are actually like deviating. Here what I am taking t naught is equal to 2k pi, so that gives us this solution, right? T naught is equal to 2k pi gives us this solution. Now see that clearly here we cannot have gamma that is independent of our like k. Like gamma, you will see that gamma for a higher value of k will have a higher value of gamma. That means like for an higher initial condition, means if you try to draw a pictorial, you will see that for different initial condition you are having different amount of means you need a higher amount of bound. Now the case is that then you can say that we can take like a very large bound, but then also what about that, means what do you mean by that large? Like if you make this k tends to infinity, then also this will remain bounded, but like it will still be, your gamma will still dependent on your initial time, right? So now we will go for studying a theorem. What is that theorem? That theorem state the linear state equation that is I just discussed. For your I request you just please write down the equation with numbers, otherwise you will not be able to track it properly. You will get completely means lost control over it without any proper referencing. So whenever I will say equation 1, most of the cases I will say equation 1 for means just to save some time, and you should refer to this particular equation 1. So clearly this is a linear state equation. So the linear state equation 1 is uniformly stable, is uniformly stable, right? When if and only if, sometimes what we do, instead of writing if and only if, we write this is also this also indicates the same meaning. If and only if there exists a positive constant gamma such that, this is very interesting, that solution is bounded by positive constant, not solution, sorry, excuse me, it is not the solution, rather it is the your, this one is your like the transition itself is bounded by gamma. And on the example that I have just discussed for the last case, you can find out that the transition is not bounded by gamma. Anyway, we have to prove this. This is equation number 4. So in order to prove, first let us consider that first suppose there exists that such a gamma exists. That means we are assuming that this gamma exists. Then we will try to see that what existence of gamma implies what. Existence of such gamma implies what. Then for any t naught and x naught, the solution of 1, see that again we need to refer it. 1 will be what? This is equal to, we know this is very standard thing. Then we know that we are using this property. Correct. So we are using this property to reach here. Now once we reach here, then we are getting this value less than is equal to gamma mod x naught. So clearly you can see that it is independent of our this uniform stability is established. Okay. Now that reverse implication, this is what we do. We consider that that gamma does exist, and then we prove that one is uniformly stable. Now we will do the reverse one, that we will consider one is uniformly stable, and then we will establish that for uniformly stable one there will be a finite gamma such that t naught and x naught such that for t naught and x naught they satisfy this equation. Correct. So what we are doing, let us consider for given an initial condition, initial time t naught, given an initial time t naught, we are having a time ta greater than t is naught. How to select this ta such that xa is such that norm of xa is equal to 1. It is not a big deal. If norm of xa is equal to 1, then that implies what? That implies phi ta comma t naught xa will be is equal to phi ta comma t naught into norm of xa. Now generally that if we check that norm a into b is less than is equal to norm a into norm b, you will see that it comes from that multiplication things. So if xa is equal to 1, there will be no chance it will become exactly equal to this one. Now initial state, let us consider that initial state xt naught is equal to x. That is means no one can stop you from selecting this try to understand that XA means don't have a prejudice in your mind that state values are distinct. Like in your last semester, when you draw face portrait, I noticed that Professor Noshkar discussed face portrait, and you got a portrait like this for a center kind of focus when your like the eigenvalues are imaginary. Like if you consider the pendulum equation that theta dot is equal to omega, omega dot is equal to minus g by L sine theta. For this, if you linearize and find out, you will see that we are getting the value, same state value for different time, right? So don't have this prejudice in your mind that state values are all distinct and they cannot repeat themselves. So you can have x like okay. So now we are selecting xt naught is equal to xa. So that will become what? That will give us xta is equal to phi ta comma t naught. It would be xa. Now this x ta and xa, this is at the two different thing, right? So xta, so what we are having? We are having phi ta comma t naught xa. That gives us less than is equal to gamma norm xa. Since your again xa, we have assumed that here norm of x is equal to 1. So this clearly indicates phi ta comma t naught is the whole state transition is upper bounded by your gamma. Now we will discuss another important concept, that is I have made a mistake. So again, the linear state equation 1, I know you can now refer which one is your equation 1. Now what we are looking for in this means that coming discussion, that like we'll discuss that uniformity means the bound exists and bound is independent of your like your initial value, but it doesn't imply that your final state will converge to 0. But what would happen if we can get an additional constraint imposed on our solution, that the solution will converge to 0 as time t tends to infinity? That is known as the case of exponential stable system. It is like if you form a set, the superset will contain all the system with uniform stability or satisfying the requirement of uniform stability, and then you will have the subset that is satisfying that your uniform exponential stability. Now the linear state equation 1 is uniformly exponentially stable if there exists this existence of this is very important finite positive constant gamma and delta. Sometimes what I will do, instead of writing there exist, I will use this symbol. This also stands for there exist, a mirror image of E, such that for T0 and X0 the corresponding solution satisfies this equation. That is equation 6. Clearly gamma is no less than unity. Moreover, gamma and delta must be independent of T0 to ensure uniformity. Why gamma cannot be less than unity? Because you can see that if you put T is equal to T0, then what will happen? This will give you 1. This will give you 1. So at T is equal to T0, it should be X0. Now this one, like norm X0 less than is equal to gamma norm X0, clearly indicate that gamma cannot be less than unity, right? Now moreover, gamma and lambda must be independent of T0 to ensure uniformity. That is very important, because again if they start depending on your T0, it will become a case that is non-uniform. So here it is a pictorial representation of what I tried to say. It is like we are having two diagrams I have drawn for you. Now you can see that these two equations, they are, both of them are like means the envelope. If you consider the slope of this envelope, the slope of this envelope is governed by e to the power minus lambda t. Here also e to the power minus lambda t, and both are started from gamma. Like both of them are started from gamma and then going to e to the power minus lambda t. So irrespective of from where your system start. So once again, if it is only this solution is means just within gamma, but not showing any tendency to converge. Obviously it cannot diverge, because if it starts diverge, it cannot be stable, and if it gives some kind of indication that even if it doesn't converge but it is bounded, it exhibits a property that it is trying to confine itself within or below certain bound, and that bound is independent of your initial time, then it is your uniformly stable system. But in addition, if it shows a convergence nature and follow an exponential envelope pattern, then it is exponentially uniformly stable. So here we will have another theorem, but I will not prove it. Rather, I left this proof for you as an exercise, that the linear state equation of equation 1 is uniformly exponentially stable if and only if there exist, this phrase is also very important, if and only, like this is both necessary and sufficient condition, right? There exist finite constant gamma and lambda such that we are having this constant are getting satisfied. Now we'll go to another theorem that is very interesting and quite like the first one. Yeah. So what is this? That suppose there exist a positive constant, finite positive constant. This indicates this is a finite positive constant. If I draw a vertical line, you should read this vertical line as such that norm of AT is less than is equal to alpha. Then state equation of system governed by equation 1 is uniformly exponentially stable if and only if there exists a positive constant, finite positive constant beta. Again, beta also less than infinity. There exists finite positive constant beta such that this line indicates such that any vertical line in this drawn in this manner indicates such that. You should read it like such that. Develop this habit of reading those mathematical symbols without much difficulties. So such that there, yeah, this is less than is equal to beta for all t comma tau such that t greater than is equal to tau. Every vertical line should be read at like such that. So now we will try to prove this equation. So phi t comma sigma, like if the state equation is uniformly exponentially stable, then from the previous theorem, what we can write? From the previous theorem, we can write this one will be means for uniform exponential stability. Like based on this theorem, we have to prove next theorem. It will satisfy this, like this equation 7. So for if the system is like stable, then obviously we can write this one for our state transition matrix, and as we are mentioning, it is uniformly exponentially stable. That is why whether we write here t naught, tau, anything else, like anything, any arbitrary term like delta, this one and this two means they should not be means affected by selection of these gentlemen, because I am discussing something that is uniformly uniform. Whenever you use this term uniform, you are actually considering a system, although the system itself is not independent of its initial condition, because the system is time varying. But if it is uniformly stable and uniformly exponentially stable, that means the system obeys certain bound. Those bounds or those equations are independent of initial condition. So whether you write sigma, whether you write lambda, delta, gamma, blah blah blah, cat, rat, bat, whatever you want, it won't change anything. So this is hold good for all t comma gamma sigma t greater than is equal to sigma. That is obvious, because we should only move in forward direction. Now for t an integration from tau to t, this will be less than is equal to this one. Here I have made a mistake. Less than is equal to this one. So if you do this integration, you will get this will give you gamma by lambda. So therefore we can establish equation 8. What is equation 8? Equation 8 is this guy that we need to prove for as means equation 1 is uniformly exponentially stable provided that there exists a finite positive constant alpha such that at norm of at is less than is equal to alpha, and if and only if there exists another finite positive constant beta such that this is upper bound by beta, right? So that we prove here. Now again we will try to do the same thing that we did for our last proof. We will try to verify it from both way. This is the direct way, like we consider that equation is like we evaluate the equation 8 and eventually got something that could be defined as beta. Now we will consider that equation 8 holds, and then we will see that whether that also yield that fulfillment of same prerequisite or not. So consider 8 holds. Now if from that we can show that phi t comma tau is equal to I minus this one. Then again this can be represented like I plus phi t comma sigma a sigma d sigma. From where this a sigma is coming, that if you do this, sorry, what? Yeah. So if you do this, obviously you will get something that is like we know so if you do, you should get minus 80 in tau, right? So we are applying this here. Now that what we are getting, phi t comma tau is less than is equal to 1 plus our that guy alpha. From where we got alpha? Because that statement was there, na? This one. So and that alpha phi t comma sigma d alpha, right? Now that is equal to 1 plus sigma beta, right? Correct. That is equation number 9. This equation 9 also holds good for any arbitrary t comma tau, provided t greater than is equal to tau. Now we'll do we'll exploit few property of transition matrix, and we'll do it in a kind of means in a clever way. We'll solve this. We'll show that we are very smart people. We can do anything, whatever we want. Means so, although from the book from which I have taken, the author is very smart. He was an IEEE fellow, but he was means not too smart to forget that means he too should not defy science or logic. But sometimes what happens in your class, there exist many people who is very kind of means when, especially when they answer or when they participate in a discussion or write means answers in exam, they have a very means like uncontrollable urge to violate all the existing rules of science and define everything by their own. They want to set up their own universe. Anyway, I am a very simple person. Means okay. So here this we can write t minus tau, that can be written like this way, that t comma tau d sigma, and this is also not a means you are not actually violating anything. See, this is not dependent on sigma, so whether means this integration will consider this gentleman as a constant. At this stage it will consider it as a constant. Now we are exploiting the property of norm, that is norm AB is less than is equal to norm A into norm B. Clear? Now but here we are playing means we intentionally, like we always know that this can be written like this. So this is true for all the value, so we just play that same thing here. But as soon as you just bring these two gentlemen in the game, then you see that they become somewhere function of your sigma. So what it will give you? It will give you something like b into 1 plus alpha, means less than is equal to b alpha beta, right? Now we consider a capital T that is equal to 2 beta 1 plus alpha beta, and define the final time t is equal to tau plus capital T, where capital T is again this one. So that yields pi t plus capital T over tau, where your sorry, this is tau plus capital T, tau is what means, basically you are doing it like means that gap is depending on t, so that will give you less than is equal to half, and that is valid for all tau, right? Now from equation 9 and 10, what we can do is that from or 9 and 10 we can write it between the time interval t plus tau to like tau plus kt, and tau plus k plus 1t. So what we are getting here is that phi t comma tau is less than is equal to 1 plus alpha beta. Then we are talking about phi t comma tau, but this time here we are taking t in this range, that is tau plus t to tau plus capital 2t. Previously it was only in this range. For the first case, your t was tau plus t. Here what we are doing, it is tau plus t to tau plus 2t. Gap remains same, but what we are observing that it is getting like your transition. If we are taking a higher, means the same time interval between two time points that are means like, how to make you understand, like when we are talking it between 5 and 10 seconds, we are getting the value of phi t comma tau, that is 1 plus alpha beta, and when we are talking about 10 to 15 seconds, then it is becoming like 1 plus alpha beta by 2. So if you are going to take it between say 40 to 45 seconds, although try to understand that 5 to 10 or 40 to 45, the gap is same, but you can see that your transition, this phi t comma tau is what? The transition. And when you are taking its norm, you are taking the norm, transition of the norm. Basically, why this transition is important, intuitively we can understand that this transition actually governs that how your initial state will be reached to your final one, final state value. So if you can impose certain bound on your transition, obviously one way is that you explain that your transition is like always within a bound that will ensure what? Uniform stability. But when you are looking for exponential, then it should also gradually converge to zero. So how it will converge? For when you if this transition exhibits a property that for first instance, first chunk of 5 seconds, what its value after say nth chunk, its value is getting reduced by 2 to the power n, then we can draw a conclusion. What is that? Like when you are doing it in this way, you are getting it, and finally between t to t plus kt to t plus 1t you are getting it. So then if you consider lambda is equal to minus 1 upon t ln 0.5 and gamma is equal to 1 plus alpha beta, then you will see that your phi t comma t tau is basically gamma exponential minus lambda t comma tau. Needless to say that gamma and your lambda, both of them are independent of your tau. They do not contain tau. So to give you a pictorial means impression, here I have drawn this diagram. You can see that it is 1 plus alpha beta within first chunk, then in the next chunk it is 1 plus alpha beta by 2, in the next chunk it is 1 plus alpha beta by 4, in the next chunk it is 1 plus alpha beta by 8, then 1 plus alpha beta by 16. It's like that. Got it? So this gives us the case of uniform asymptotic stability. Uniform exponential stability. What is uniform asymptotic stability we will discuss later. Now obviously if you just considering shortly the for LTI system, obviously the things will become means this phi t comma for LTI, what you will have, what we observed in our last video. For LTI, phi t comma sigma is equal to what? A to the power t minus sigma, right? So this uniform exponential stability is equivalent to claim that this one is finite, or in other way, for LTI, if you evaluate this integral and you find that integral result is finite, or better to say that integration of this exists, then you can say that it is finite and it is uniformly stable. Uniformly exponentially stable. Another thing that in case of LTI, don't you think that using uniform is also meaningless? Think about it, and before you watch the next video, In next video, you may find some more argument in favor or in opposition to this particular statement. Means that will help you to conclude. But I want you to be somewhat like means you should be able to apply your own logic to understand that why this one is like same uniform in case of linear time invariant system. Means whether do we need a separate concept of uniform stability for linear time invariant system, or uniform what is kind of superfluous in that case. That you just need to consider, like whether it is redundant or it is required, this adjective. Obviously you can keep on adding adjective, like when you try to write a recommendation for yourself. I observe that you means try to like means find all sorts of positive adjective and try to write means to means like justify your candidature or your means make your recommendation strong, like he is good, he is honest, he is means even a very funny thing is that some people write he is honest, he is not dishonest, he is very honest. It's like that. So, but in this case also, you just need to find out that for LTI, whether we need uniform or using uniform is just a redundant thing for LTI system. Next video, I'll start from this theorem. Next theorem.